What if I told you that over 50% of a farmer's annual revenue is absorbed purely by irrigation costs? Well, that's the reality, and in today's video, I'm going to be demonstrating how multi-variable recurrent neural networks can be used to better forecast electricity prices and how farmers can use this technology to minimize their electricity bills. So the overhead irrigation costs for farmers in Australia are essentially split into two different buckets. The first bucket is the cost of water, which is essentially commoditized, meaning farmers must own a certain amount to be able to pump that amount from their water source, be it a river or an estuary or a dam. The second bucket is the cost of electricity, which varies dependent on the time of year, time of day, how much load is on the network, etc. Specifically in South Australia, where we have such high renewable penetration. Now, electricity is sold to farmers through the terms of their electricity plans. Now, whilst most farmers are on a residential plan, meaning they adhere to peak and off-peak rates defined by the retailer, this can be very expensive, costing up to $25,000 a month just to irrigate their crops. Due to this, a lot of farmers are changing to what's called the spot market plan, which is used by a lot of industrial and large-scale consumers. Now, this allows our consumers to take advantage of the negative prices during the day, as shown by the figure, which happens when a lot of the solar and wind comes into the grid. But the trouble a lot of farmers face is, once they're on this plan, how do they know what time to irrigate to mitigate their costs? And that's when they turn to a company called AEMO, which is the Australian Electricity Market Operator. Now, AEMO uses price forecasting to forecast this spot price, as shown in the figure on the right. Now, this is used to inform their demand to schedule their generator supply. So if they can forecast their demand, they will know what generators to schedule to generate during those periods to meet supply and demand. Now, the only trouble is this is only one day in advance, so it doesn't really help our farmers much. And although this forecasting model is not open source, the data that feeds into it is via the OpenNEM web API. Now, this OpenNEM web API supplies 25 years of data and has available features such as time, being in year, month, day, and hour, as well as network demand in megawatts and price in dollars per megawatt hour. So that begs the question, how can we utilize the available data to forecast power prices in advance to better inform our farmers? And this is where machine learning comes in the form of recurrent neural networks. Now, recurrent neural networks were first conceptualized by John Hopfield in 1982 with his Hopfield model, which was designed to store and retrieve patterns from historical time series data. But it wasn't until 1997 with the long short-term memory variant that we could really retain that information over several steps. Now, this model is considered to have long short-term memory as it uses previous inputs to make current time step decisions, as we can see by the figure on the right. Now, due to this historical trend retention, RNNs are characteristically used for things such as natural language processing and price forecasting, where we're using that historical data to inform our decisions in the present day. And you're probably thinking, price forecasting, exactly what we're looking for. So now we have our data, we have our architecture, let's build a proof of concept. So using these inputs, I've created a multi-variable RNN for power price forecasting in South Australia. Now, the input data I'm using is the 2022 sample data from AEMO's OpenNEM web API, which includes 8,760 or 1 year's worth of data, as you can see on the right there. Now, I used this input data to build a pretty standard long short-term memory model. The steps I followed was to extract my features into a data frame, pre-process this with a min-max scaler, generate my sequence, which I used a length of 24 hours, build my long short-term memory model using 50 LSTM units and one fully connected layer, compiled this model using an atom optimizer and the mean squared error loss function, fit the model to my training data, and then evaluated my losses to assess performance. Now, the outcome from training this model was some pretty low evidence of overfitting, as you can see from the mean squared error per epoch plot on the bottom right. Now, my vision for improving this model for the long term is to combine the model with a CNN or convolutional neural network to enable this extended future forecast to have higher accuracy. But again, you're probably thinking, what does this model look like for our farmers? The easiest way to effectively display this information for farmers is via a calendar. So essentially what we've got here is a user interface for the next week forecasted ahead. And for every hourly time slot, we've put in our forecasted hour price, which has then been graded on a green to red scale to make it very easy to perceive what time should we water and what time shouldn't we water to minimize our cost. The societal impact of this application is that we have reduced electricity bills for the farmer, which is a big tick. We also have reduced strain on the electricity network by absorbing all that excess solar and preventing the use of our interconnectors, whilst also increasing the advancement of AI and ML in industry applications, which is exactly what we want to continue doing to remove this nervous stigma from AI technology, which is exactly what we're after moving through the 21st century. So overall, I hope you enjoyed. Thanks for watching, and I'll see you in the next video.